Okay, so in this video, we're pretty much just going to introduce a definition that we're going to need during our discussion of sampling. And then we're going to see some examples to try and get the hang of it. But that definition is the definition of band-limited signals. Okay, so before we get to the mathematical precise definition, let me just draw two pictures to kind of motivate it. So the first one is going to be a function of time. Well, it's actually going to be four pictures, but two functions. And I'm just going to draw this randomly. Okay, who knows? Maybe that's my x1 of t. And if we look at its Fourier transform, again, just completely making this up, just so we have something to look at, let's say the Fourier transform looks something like this. Okay, and by this drawing, I'm trying to show that the function kind of never gets to zero in these directions. Okay, so you can think of it maybe exponential decay in both directions. It never actually hits the omega axis. And now in contrast, let me draw another function, again, just completely making this up. Okay, who knows, maybe it looks something like that, x2 of t. And let's say that its Fourier transform looks something like this. Let's say it actually starts, it equals zero, and then who knows, it does something in between, and then it equals zero again forever after that point. Okay, let's say this is x2 of omega. Okay. So what are the two things I'm trying to highlight in these different Fourier transforms? Well, in the first one, I'm trying to say that the function, as omega gets large or small, it never quite ever gets to zero forever. Okay, there's always non-zero values as omega gets really big or really small. In contrast, the second function, okay, I'm trying to show a picture of something where outside of a certain range, like here, the function is always zero forever after, outside of some window. And this is actually what the definition of band limited is going to be, that I can put some window around my function, around my Fourier transform, so that within that window, who knows, the function can do anything. Maybe it equals zero some places, maybe it doesn't. But outside of that window, the function definitely equals zero. The Fourier transform definitely equals zero outside of some window. In other words, the Fourier transform is limited to some frequency band around the vertical axis. That's going to be band limited. So in these two pictures, x2 of t would be band limited because I can do what I just said, but x1 of t is not, because no matter where I put some window, there's always places outside that window where the function is non-zero. So x2 of t is not limited to some band. It goes either to plus infinity or minus infinity. It's non-zero at some point in either direction. In this case, both directions. Turns out you only need one direction, but yeah, x1 of omega is not band limited, okay? Because again, no matter what window I put around it, there's always places outside that window where the function is non-zero. So this was just supposed to motivate the mathematical definition a little bit with a picture, okay? And let me just put into words what I just said, the properties I'm trying to highlight here. So x1 of omega has non-zero values forever as omega goes to plus or minus infinity. Okay, and we'll see more examples to get exactly the precise definition of band limited later in the video. Okay, but for now, that is a true statement about x1, and x2 of omega actually equals zero outside of a window around the vertical axis. So these are the two properties of those Fourier transforms I wanted to highlight. And that's going to lead into our definition now of what band limited means precisely. Okay, but I wanted to start with sort of an overall picture example just to, get your mind in the right place, because sometimes when you see just an abstract math definition, it's hard to process. Okay, but here it is. So a signal x of t is band limited if what? Well, if there exists sometimes we refer to it as a maximum frequency, but I'm going to put it in quotes because we'll see some examples and we'll get to know what that really means a little more. So exists a maximum frequency, which I'll call omega sub m, that's positive, such that, okay, the Fourier transform of x of omega equals zero whenever the absolute value of omega is greater than omega c max. Okay, so at first glance, this might not seem to be saying exactly what I said before, but it actually is. All this is saying is there exists a maximum frequency, and I'll label it in my picture. Let's say that is my omega sub m, so that the function equals 0 whenever omega is greater than omega max in absolute value. What does that mean? Well, that just means whenever omega is a lot bigger than omega max, or whenever omega is a lot smaller than negative omega max, right? That's all that absolute value is doing. This condition is really the same as whenever omega is greater than omega sub m, or omega is less than negative omega sub m. In either case, the absolute value of omega would be greater than omega sub max. And what does it look like in a picture? Well, it's just saying if I draw these dotted lines here, that within those dotted lines, who knows what can happen? Maybe x2 of omega equals 0 some places there, maybe it doesn't. We don't care. We just care whenever the absolute value of omega is greater than omega sub max. In other words, whenever omega is greater than omega max, so on this side, or whenever omega is less than omega sub max, so on this side, we need our function to be 0. Okay, so that's all band limited saying. It's saying there exists these bars I can draw, some window, some frequency band around the vertical axis, so that within that band, my function, my Fourier transform can do whatever it wants, but I just have to guarantee that outside of that band, the function always equals 0. In that case, we say that x2 of t is band limited. And you can see that x1 of t is not band limited because no matter where I put those bars, outside of them is always some place where x1 of omega is not 0. Okay, so that would break this band limited definition. And just looking at it, I mean, intuitively band limited, this function is not limited to any frequency band. It's non-zero forever as omega goes positive or negative. So it's very not band limited. Versus this function, just looking at it, of course it's band limited because it equals 0 outside of this window, but just looking at it, I mean, it's limited to this frequency band, right? It's only non-zero in this range. Okay, so that's all band limited saying. This is the precise mathematical definition. Okay, so let me just write down what I said about that example. So in the above example, okay, so x1 of t, as we were just saying, is not band limited, right? Because I can't put any bars and have my function be 0 outside of it, right? There's always places outside of it where it's non-zero. Oops. Yeah, okay, but my function x2 of t is band limited. Okay, because I can put these bars here and the function 0 outside of them. Okay, that's a band limited movement. All right, great. So let's do some examples to really get the hang of this. So first one is sync of 3t, is that a band limited signal? Is sync of 3t band limited? So what do we have to do to figure this out? Well, we have to look at the Fourier transform and try and decide, is there some frequency band, some window around the vertical axis so that my function, the Fourier transform of this function is 0 outside of it? Okay, so let's just look at these two functions. So we have sync of 3t, looks something like this. Okay. Kind of tough to draw. Okay, so this is sync of 3t. And what's the Fourier transform of sync of 3t? Well, this is a Fourier transform pair we've seen, and it's just the rect function. Okay, so we have pi over 3 rect of omega over 6. That's the Fourier transform of sync of 3t. We found that Fourier transform pair. Okay, so this is just a rect function that looks like that. Okay, and you can see visually, of course, rect is a band limited function, or sync of 3t is a band limited function because this function rect is 0 outside of this window. Okay, and so sync of 3t, even though sync of 3t is non-zero forever as I go either direction in time, that's fine. That has nothing to do with band limited. To talk about band limited, we take the Fourier transform, looking in the frequency domain and saying, does there exist some band, some frequency window around the vertical axis so that my function is 0 outside of it? Clearly that's the case for rect. So if we take omega m to equal 3, then this Fourier transform equals 0 whenever the absolute value of omega is greater than omega max equals 3. Okay, because look, I can just draw these dotted lines and my function is 0 outside of them. Okay, rect is 0 forever outside of that frequency band. And so that tells us that sync of 3t, sure enough, is band limited. Okay. Let's do another one. Okay, so what happens if x of omega equals u of omega? So if that's true, is x of t band limited? Let's just draw what that looks like. So x of omega looks like this. It's 0, and then it goes up to 1. Is this a band limited function? Well, we have to say if it were, if x of t was a band limited function, that would be saying that there exists some window where x of omega equals 0 outside of that window. But no matter what window I choose here, there's always going to be some place on the right side where x of t is non-zero, right? Where x of omega is non-zero. Because x of omega equals 1 as omega goes to infinity. It just keeps equaling 1. So no matter how wide I make this function, still x of omega will equal 1 to the right of whatever my right-sided bound is of that window. Okay, so x of omega is not band limited. Or sorry, x of t is not band limited. We say the time function is band limited or not usually, but we're just saying x of omega, there's no window I can put around the vertical axis so that x of omega is 0 outside of that window. So let me just write that. So there does not exist omega sub m greater than 0 such that x of omega equals 0 when absolute value of omega is greater than omega sub max. So x of t is not band limited. Need some more room. So x of t is not band limited. Okay. Let's do another one. So how about cosine of 3t? Is cosine of 3t band limited? Well, let's check. What's the Fourier transform cosine of 3t? Well, again, this is a common Fourier transform pair we know about. This is just pi delta of omega minus 3 plus delta of omega plus 3. Okay, so what does that look like? Just looks like this. Got two delta functions at plus or minus 3. They have height pi. Okay, so clearly we can take omega max to be 3 because outside of those dotted lines, the function just equals 0. Okay, both those delta functions equal 0 except at plus or minus 3. So if we take omega m to equal 3, then x of omega equals 0 whenever the absolute value of omega is greater than omega sub m, which is 3. Okay, so cosine of 3t is band limited. Right, and again, I mean, you can just look at it. Of course, there's some window. You don't have to take omega m to be like as tight of a window as possible. I mean, technically from the definition, I could take this to be my window, and it's still 0 outside of those bars as well. Okay. All right, now let's do one more. Here's the last one. So if x of omega is as drawn below, I'll draw in a second, then is x of t band limited? And let me draw it. So let's say it looks like this, -5 up to 2. And I don't know, I'll just draw some random thing. Doesn't really matter. Okay. So let's say that is my x of omega. So if that's x of omega, is x of t band limited? And here you might say, this is why I put maximum in quotes and maximum frequency. You might say, oh, well, I'll take 2 to be the maximum frequency. It's the biggest frequency, right? But then if I take this to be omega max and I put negative omega max, which would be -2, you can see that doesn't work for our definition of band limited, because over here the function's not 0. X of omega equals 0 outside of that window. Okay, and so when we talk about that max frequency, omega sub m, what we really mean is maximum in either direction. So what's the largest absolute value of a frequency where omega, or where x of omega is non-zero? You can see in this case that would be 5. Okay, so if we take omega m to equal 5, okay, then this would be negative omega max. I could go out to 5 here, and this would be omega sub max. And now that works for our band limited definition because our function is 0 outside of that window. It's limited to that frequency band. So if omega sub m, if we take that to be 5, then x of omega equals 0 whenever absolute value of omega is greater than omega max, which was 5 here. Okay, so x of t is band limited. Okay, so that's why I put maximum in quotes, because it's not maximum as in greatest without taking absolute value, because that would be 2, but that doesn't work for our band limited definition. Right? Again, the function 0 outside of that window. That's fine. We can just take omega m to be the maximum magnitude or absolute value of any frequency where x of omega is non-zero. And in that case, we'll just take it to be 5. And you can see, sure enough, that works for our band limited definition, because outside of this window, the function is 0 forever. Okay, so that means x of t is band limited. All right, so I think these examples kind of cover, most of the different cases of band limited or not band limited signals we'll see. So hopefully that makes the definition make a lot more sense. It's really not a complicated definition, but the actual mathematical form of it sometimes can be confusing. So hopefully all of these pictures and examples makes it clear. Okay, and this definition is going to come up when we talk about sampling, which we're going to do in the next couple videos. So great, that's all I had for this video. I'll see you in the next one.